India is currently executing an aggressive expansion of elevated transport infrastructure, building across varying geographies at maximum capacity. State planners and civil engineers are actively constructing over 1,500 kilometers of new elevated structures. This volume of construction is driven by simultaneous megaprojects, including the Regional Rapid Transit System, the Mumbai-Ahmedabad bullet train, and expanding metro networks across Mumbai, Chennai, and Bangalore. While the finished viaducts appear as continuous ribbons of monolithic concrete, they are actually discrete segments, assembled piece by piece in midair. Lifting and locking these immense concrete blocks into place introduces massive, dynamic tensile loads. Managing those physical forces is the primary engineering constraint on site. Executing thousands of kilometers of elevated transit demands a construction pace that pushes traditional assembly methodologies to their absolute physical limits. To meet these strict timelines, engineers rely on a mandatory construction technique known as segmental launching. A launching girder operates overhead, lifting massive precast concrete segments. As each block is hoisted, immense gravitational loads transfer entirely onto the temporary steel framework. This apparatus remains stable only because highly specific structural connections precisely anchor the active girder to the fixed pier below. The critical hardware carrying this load at the bottleneck is the post-tension, or PT, microalloy bar. By deconstructing the exact specifications of Bolin's indigenously manufactured PT bar systems, we can see the exact hardware that makes this scale of construction physically possible. The safety of these massive public transit corridors ultimately depends on the strict millimeter-level tolerances of these hidden microalloy connections. Moving from the overall span of the viaduct down to the individual load points, we arrive at the pier-to-segment junction. This specific junction demands extreme low-tolerance applications. It manages the active forces of girder lifting, segment stitching, and locking the formwork tightly in place during the pour. This schematic details the Bolin post-tension bar system. The threaded rod passes through the structure, secured by specific anchoring accessories. The hex nut and threaded coupler lock the bar, transferring heavy tensile loads from the suspended segment directly into the fixed pier. Because these engagements occur hundreds of feet in the air on active schedules, they must be established quickly while allowing zero margin for slip loss or load reduction. At these high-stress junctions, the hardware serves as the primary load-bearing lifeline for the structure, requiring flawless mechanical performance under dynamic conditions. The geometry of the connection explains the mechanics, but the raw tensile forces require specialized metallurgy to prevent snapping. Bolin manufactures a range of cold and hot-formed, fully threaded bars, utilizing a high-yield grade 930-1080 steel. These are not standard rebars. To handle localized megaloads, these microalloy bars are scaled up to a massive 100 millimeters in diameter. When specifying structural steel for lifting operations, the determining performance metric is how the metal behaves at its absolute failure threshold. This chart shows the stress-strain curve for Bolin's PT bars. The material is engineered with a strict requirement. It must maintain a minimum elongation of 6% at the breakpoint. That 6% threshold, located in the plastic deformation zone, guarantees structural ductility. Ductility means that under critical maximum stress, the steel will visibly stretch and yield rather than suffering an immediate brittle fracture. By designing the steel to stretch before breaking, engineers on site get a clear, visual warning of overloading long before a catastrophic failure occurs. With the internal metallurgy established, the functional performance of the bar relies on its external geometry. For segmental launching, a continuous, fully threaded profile is a strict operational requirement. The hot-rolled thread runs the entire length of the bar, providing site crews flexibility to engage nuts and couplers at any exact location required. There is a secondary advantage engineered into the interaction between the thread and coupling accessories. As the nut threads onto the bar, the specific geometry automatically clears out cement dust, grit, and debris from the grooves. The continuous thread operates as an active defense mechanism that reduces installation time and resists the aggressive, debris-heavy environment of a concrete pour. While segmental launching uses these bars as temporary framework, their high-stress tolerances apply directly to permanent structural implementations. Engineers embed these exact same microalloy bars deep into concrete to function as seismic arresters and shear keys, securing critical structural connections, and hold-down bars for stub columns. Beyond zooming out from the individual threaded connection, managing a massive active construction site introduces a different kind of constraint: logistics. Historically, the availability of these highly specified microalloy bars has been scarce in India, forcing contractors to rely on imported materials with long, unpredictable lead times. Superior metallurgical specifications cannot advance a project if supply chain delays bottleneck the critical path of construction. Bolin addressed this gap by establishing a local supply chain, operating as the first and sole manufacturer for high-strength stress bars entirely made in India. Localizing this production requires strict quality control, supported by ISO 9001, 14001, and 45001 certifications, ensuring the domestic raw materials meet precise global engineering standards. Transforming complex international procurement logistics into a predictable local engineering variable is exactly as critical to the project as the yield strength of the steel itself. The direct result of this localization is visible across flagship megaprojects like the MMRDA's Mumbai Metro Line 9. By eliminating procurement delays, contractors can meet their aggressive turnaround times and keep the launching girders moving. Crucially, this execution speed is maintained without compromising the strict structural tolerances required by the heavy post-tension framework. From the macro logistics of the supply chain down to the continuous thread geometry and the strict 6% elongation threshold, every variable is carefully controlled. Elevating thousands of kilometers of transit across the country requires mastering both the physics of concrete and the logistics of structural steel. Ultimately, the rapid expansion of modern infrastructure relies entirely on the microscopic precision of the hidden connections holding it all together.